Okay. Hi everyone, welcome. My name is Brad Olsen. I'm an assistant professor here at MIT in the Department of Chemical Engineering. It's a real pleasure to have the opportunity to speak with all of you today as part of the Neutrons and Soft Matter Science course put on by Oak Ridge National Lab. Thanks, Mayun, and to all the organizers for the opportunity to speak. And hopefully we'll have an opportunity to learn something. And please feel free, of course, during the lecture to interrupt with any questions that you might have in the chat window or any other mechanism that you feel appropriate. The topic for today is on applications of neutron scattering to polymer gels. Before starting, I guess let me take time to pause so Mayun can get feedback on the quality of the sound and whether everyone has a good connection. Okay, wonderful. So I want to start out by talking about what is a gel. And I think there are a number of different definitions out there in the literature. I've extracted one from Richard Jones from his textbook on soft condensed matter, which says that a gel is a material composed of subunits that are able to bond with each other in such a way that one obtains a network of macroscopic dimensions in which all the subunits are connected by bonds. A gel has mechanical properties characteristic of a solid, even though it is structurally disordered and indeed may contain a high volume fraction of liquid solvent. Right, so I think this definition of a gel contains a lot of things that are very, very important in differentiating gels from other types of materials. And the first one is that we intuitively know gels to be solid materials or solid-like materials. And then certainly, since all of us are involved in the characterization of soft materials, and many of us in the study of mechanics of these materials, we know that often these materials are viscoelastic. So certainly the concept of a gel being a solid is something worth revisiting, but it has some solid elastic-like properties. Gels are formed by networks of molecules. Essentially, they have some sort of macroscopic connectivity between different molecules across large distances, which imparts to them these solid-like properties. And one of the big things that differentiates a gel from other types of solid-like materials is that a gel is very high in solvent. And this concept that it's high in solvent means that it has some concept of having liquid. In particular, it can have certain transport properties that very much resemble the liquid solvent itself, but macroscopic mechanical responses more like a solid. And so this is an interesting category of materials that has a wide variety of different applications, many of them in our everyday life. So examples, I've shown on this slide several examples of gels in everyday life that we encounter. The upper left-hand corner, one of my favorites, and I think one of the favorites of my group, is this sort of multi-layer jello, which is a fantastic food for us on X-ray and neutron scattering beam time trips. But this is, I think, one of the most intuitive gel materials, something that many people eat. It has solid-like properties, but is mostly water by composition, right? And a small amount of gelatin transforms liquid water and sugar into essentially a sugar solution with food coloring into a solid-like material. Another example of gel in everyday life is personal care products. I've shown here an example of toothpaste, which is just one example. Things like hair conditioner, various forms of shampoos are also other examples of gels. These materials, in particular physical gels, can undergo liquid to solid transitions under shear, which gives them the necessary properties for use. For example, it's fascinating when you think about it deeply that toothpaste can be squozen out of a tube, but then when it sits on top of sharp bristles of a toothbrush, it doesn't flow down into those bristles. Right? So here's a material that's capable of transitions from liquid-like behavior to solid-like behavior, depending on how it's processed. And again, it's predominantly water based on its composition. Another example from food is things like jelly, so a different type of compound doing the gelling, pectins rather than gelatins. And then finally, an example from orthopedics, the gel cushioning insoles for shoes are an example of where we see gels in use here for their ability to be soft and cushioning. So essentially, this highlights another aspect of gels, that while they're solid-like materials, their stiffness or their modulus is relatively low compared to other categories of materials, such as solid polymers or metals or ceramics. Gels will typically have a modulus all the way down from in the range of 100 pascals up to maybe hundreds of thousands of pascals, or approaching 1 megapascal is a typical range. So a very wide range of modulus, but much softer than most of the other structural materials that we're used to using and considering. Now, for a number of different reasons, gels have also attracted a wide variety of interest in advanced research topics. Many of these are biomedical research topics due to the similarity between gels, in particular hydrogels, and the native tissues in the body. So native tissues are also largely composed of water. Many of our tissues are 70% or sometimes somewhat greater composition of water, mixed with proteins and polysaccharides, lipids, and other compounds. And so this makes them compositionally similar to a number of different hydrogels, and so has attracted interest in engineering hydrogels that can be incorporated with and mesh with these tissues. Furthermore, the tissues and hydrogels will also have a similar range of modulus in many cases, which makes them which also makes it attractive to use hydrogels in biological systems. So one of the widest applications for hydrogels where they've been investigated is for use in drug delivery. And I've shown a table here excerpted from a recent review on developing hydrogels for controlled release formulations. And what this table shows that I think is interesting is how, by tuning different properties of gels, essentially causing them to respond to their surroundings, there are a wide variety of different mechanisms by which pharmaceutical compounds can be released from hydrogels. And I think these mechanisms illustrate what's interesting about hydrogels as materials that motivates our use of neutron scattering to characterize their structure. So looking at the first mechanism on this slide, it says in very, very small print above the arrow, diffusion, essentially that a compound can be loaded into a hydrogel and allowed to diffuse out as one means for releasing that compound. And the interesting science behind this is that when you have small molecules in a hydrogel, the hydrogel has pores of a size much, much larger than the small molecule. And essentially what's been found experimentally and modeled theoretically is that the diffusion of a small molecule through a relatively large pore in a hydrogel will be almost the same as the diffusion of the molecule just in the solvent. There's a relatively small slowing down of the rate of transport of these systems. And so you can achieve relatively rapid transport of small molecules through a structure with solid-like mechanical properties by using a hydrogel, which is something that's difficult to do with other categories of materials. The second arrow here indicates swelling, and so you can imagine changing the solvent composition of a hydrogel, essentially increasing the space in the network or shrinking the space in the network. And by doing this, you can cause, for example, if you have very small spaces in the network to hinder diffusion, then increase them. You can actually cause diffusion to increase and have a triggered release of a compound based on swelling of a hydrogel. Or the converse, you can actually cause a hydrogel to deswell and essentially decrease the concentration or the volume of solvent within the hydrogel and actually force molecules out. And so either swelling or deswelling can be used alternately as a way to trigger release of molecules. And this starts to hint at the responsive nature of a hydrogel that can potentially, based on changes in its solvent composition dynamically, that can be used to start to engineer smart materials. And this smart materials and responsive aspect is one of the huge attractive features of hydrogels. Third down is degradation, so essentially now modulating transport by allowing selective chemical or physical degradation of the crosslinks in a hydrogel. And so again, we're changing the characteristic size and structure of the gel in order to tune transport from a regime with small pores where transport is restricted to a regime in the partially degraded gel with large pores where the gel is now expanded. Both this degradation and swelling, as I've alluded to, can be triggered by stimuli, and so you can produce gels that will respond with changes in the release of molecules to things like temperature, pH, ionic strength, light, and now many more complex responses. For example, triggered release based on a biomolecule. And then further down, you can also think of functionalizing gels with different chemical functionalities. For example, affinity binders, as indicated here, or chemical bonds, indicated here, that over time will slowly release a compound due to physical or chemical degradation of the bond in the network. And this, once the compound is released into the network, again, because it's very open with very rapid transport, you can see rapid diffusion of a material out of a hydrogel. And then finally, more exotic approaches, such as multiple carrier approaches, where you can embed structures into hydrogels. So essentially, prepare a gel around some other type of nanoscopic or mesoscopic material, where you have now a hierarchical structure within the material that can accomplish the release of the pharmacokinetically active compound. So another area where gels have attracted a great deal of interest in biomedicine is tissue engineering. And in this case, the similarity in the mechanical properties between the mechanical properties of the gel and the composition of the gel and native tissues directly provides us with inspiration in terms of using synthetic materials to recreate natural tissues, or to provide matrices for the regrowth of natural tissues using cells. And so this type of engineering really requires careful control over two things. One is the biochemistry of the polymer hydrogel. And so this is shown on the left by a figure excerpted by a review from Jeff Hubbell's group, Nature Biotech, in 2005. And what they show here is that the presence of physical signals, which means signals chemically incorporated into a hydrogel network, or soluble signals, which is proteins or small molecules which are dissolved in or non-covalently associated with the network, both interact with cells, and through interaction with receptors on the outside of cells, these signal to cells to affect their behavior. Things such as growth, differentiation, adhesion onto a surface, the formation of vasculature, or formation of complex tissue structures. And so being able to produce a hydrogel with the right biochemistry is very important to control the cells. I think around the same time, there was a pioneering paper by Adam Engler, who is currently in Dennis Disher's group. And Disher's group was looking at using polymer engineering concepts in order to control the behavior of cells. And in this paper from Cell in 2006, they demonstrated, one of the earliest demonstrations, that changes in the mechanical properties of a hydrogel can actually be used to tune the differentiation of stem cells on a surface. So what they did was grew hydrogels on a two-dimensional elastic, grew cells on a two-dimensional elastic substrate. And in the left column here, they grow cells on a relatively soft substrate, while in the right column here, they grow cells on a much stiffer substrate. And what they show is that the stem cells show characteristics of different cell types depending upon the stiffness of the support on which they're grown. So the cells grown on the softest support tend to differentiate into neuron-like structures, whereas the cells grown on stiffer supports tend to form muscle-like structures. And this is corresponding roughly to the modulus of the tissue in which the cells would typically be found. And so what Disher's group infers is that the modulus of the surface sends cues to the cells about how they should differentiate and what types of phenotypes they should take on. And so this suggests to us that polymers and material engineering is also very, very important for controlling the behavior of cells in the preparation of tissue engineering implants. So moving away from biomedicine, I also thought an interesting example of how gels are impacting modern technology is actually in the work of one of your previous speakers, Professor Tim Lodge. And this is an example of a paper that he collaborated with Professor Dan Frisbee at the University of Minnesota with, where they actually engineered gels based on ionic liquids now instead of based on water, as is commonly seen in the biomedical literature. So the Frisbee groups and the Lodge groups use a triblock copolymer, polystyrene, polyethylene oxide, polystyrene, and then mix this with ionic liquid, which selectively segregates into the polyethylene oxide block of the copolymer. And again, because the transport in the solvent of the gel, in this case the ionic liquid, is diminished only very, very little relative to that in the bulk solvent, they're able to get very rapid ion motion within this gel. And so they can produce capacitors, which is shown here in the lower left. And then they also use organic semiconductor, P3HT in this case, in order to produce a channel. And they use this to produce an organic transistor, which has as a gate dielectric the ion gel. And so they're able now to start to produce organic electronics with different soft and flexible materials using these ion gels due to their capacitance and high rate of ion motion, which is again uniquely enabled by the fact that you have fast solvent motion within a solid-like material when you look at a hydrogel. And then finally, this is the last sort of high-tech example I'll show, which is the application of gels for sensors and actuators, in this case soft actuators. So I've shown here a couple of pictures of robots that use soft actuators. For example, this Albert Einstein robot, which uses soft materials in order to create actuation, which generates facial expressions. And examples from, for example, Rich Spontak's group at NC State, where they have looked at soft actuators where they use copolymer hydrogels and then apply electric fields to these materials, and the electric fields create deformation in the material, which causes actuation. And because the material is a gel, you have a relatively small amount of force required to do the deformation, and you essentially create a soft actuator, which can more accurately or more sort of faithfully reproduce the facial expressions and motion of things like muscles. So these sort of soft actuators are very, very interesting for when instead of actuating large or heavy loads, we were trying to do fine motion of for example, soft structures. So given hopefully by this point I've convinced you that there's a fantastic amount of interest in applying gels in high-tech, in consumer products, in food, in biomedicine. And so what I'd like to do now is talk a little bit about the science of gels, and then where neutron scattering can inform and help to move forward our understanding of these materials. So I want to start out by focusing a little bit on the simplest type of polymer gels, which is probably simple polymer networks, just flexible molecular strands that connect chemically cross-linked or physically cross-linked junctions within a material. And then go on and really expand out to many more of the types of networks that can be synthesized. I think polymer networks are a great place to start because relative to many of the other types of gels, we have some very well understood and foundational theories that explain to us properties of interest about their synthesis, their mechanical response, and so this is a good place to focus to sort of understand what the questions are that we want to ask about gels, and what some of the answers are in one example system to guide our thinking about other systems. So starting with this polymer gel, essentially I show at the top of the screen two molecules, one trifunctional and one difunctional. And so this is you can consider this schematically as an illustration of what the chemistry might look like in a gel, where the red groups can react with the blue groups, or sort of the Pac-Man groups can react with the pieces of pie in order to form a coupled bond. And so because we have both linear and trifunctional molecules, then we can form a polymer network upon reaction of these molecules together. Essentially, the average functionality of our molecule is greater than 2. So as we start to grow gels, our molecules will polymerize. And there are several different theories for this chemistry. I've shown here just one example, the Carruthers theory for gel point, which essentially shows as you convert these linkages, you can calculate the degree of polymerization as a function of conversion. And what you see is that depending on the functionality of the multifunctional junction, I show here in blue functionality 3, which is the case illustrated. As the conversion increases, eventually you reach a point at which the degree of polymerization blows up. Essentially, the molecule becomes infinitely large or macroscopically space-spanning. And this is the point at which you form a macroscopic network that spans across an entire sample. And this is capable of transmitting mechanical force across a sample and leads to a transition from a fluid-like state, essentially a polymer solution of branched polymers, to a solid-like state. This large molecule that's connecting all the way across a sample, essentially macroscopically percolating across an entire sample. So there are two sort of primary theories of polymer gel mechanics. I think the most common theory, and perhaps the original theory, was the affine network theory, which says that we can consider now our macroscopic network. Let's for just the sake of putting a picture in our mind, consider the network here that I've illustrated on the lower left of this slide. And then when we deform this network, we assume that all of the molecules deform according to the macroscopic applied deformation. So essentially all of the molecules move with the bulk material without any internal relaxation of the position of network junctions. And so this is what we mean when we say affine deformation of the material. In this case, then the free energy of deformation can be written as the number of molecules, that's delta F, can be written as the number of polymeric strands in the gel, multiplied by KT, the Boltzmann constant, times temperature, divided by 2, and then times the extension ratio squared in each of the dimensions, lambda x squared, lambda y squared, lambda z squared, minus 3, where each of these lambdas is 1 for an undeformed structure, and greater than 1 or less than 1, depending on the value of the deformation in each given dimension. And so when one calculates what the shear modulus will be for this material, the shear modulus down here is G. We find a very simple formula, that the shear modulus is equal to the number of elastic strands times kVt, the Boltzmann constant, times temperature, divided by the volume of the system. And so if we recast N over V as the density of elastic strands in the system, then we can say that the shear modulus is simply proportional to the density of elastic strands in the system times kVt. And so the affine network theory tells us that a stiffer polymer gel will have more polymer strands per unit volume, whereas a softer polymer gel will have fewer polymer strands per unit volume. And I think it's surprising how few variables come into this in a direct sense, because I think everyone intuitively thinks, well, if I increase the concentration of polymer, won't the stiffness of the network go up? If I change the molar mass, won't the stiffness of the network change? And all this is certainly true. As one increases the concentration of polymer, of course, the density of elastically effective strands goes up, and so that makes intuitive sense. As one increases the molar mass of the polymer, remember that the gel is prepared, when you consider this, you most likely are considering this at a fixed concentration of polymer in terms of grams per volume, for example. So if you increase the molar mass of the polymer in terms of grams per mole, and then keep the grams per unit volume, the mass concentration the same, then what you're effectively doing is decreasing the moles of polymer strands per unit volume. And so a network with longer polymers will effectively be softer at a given polymer concentration, which again is consistent, I think, with what we intuitively know from polymer science, from the theories of sort of stretching individual polymer chains. The other network theory that's been developed is the phantom network theory. So the phantom network theory has a significant change from the affine network theory, that it allows junctions within the gel to relax. So the gel can undergo internal relaxation, which minimizes its strain energy, and therefore the overall modulus is predicted to be lower. So the change in free energy has a similar qualitative form to that found in the affine network theory, but when you go through and calculate the modulus, what you find is the modulus is again equal to the number of elastically effective strands times kVt divided by volume, but now multiplied by a factor 1 minus 2 over F. And here F is the functionality of the network cross-linking points. So in our previous example from the last slide, F was equal to 3. And so you have 1 minus 2 over 3 as this coefficient. And so essentially the more highly functional the junctions, the less relaxation that can happen in the gel, and you have a modulus predicted to be closer to the affine network theory. Whereas if you have a lower functionality, then the phantom network theory predicts a larger effect of relaxation of network junctions to minimize strain energy, and you are predicted to have a lower modulus. What you see, though, I think the commonality between both of these is that this density of elastically effective chains, with some factor accounting for relaxation, is really what's governing the modulus of these materials from ideal Gaussian polymers. So one of the other properties that's very important and interesting, as we saw looking at some of the concepts for controlled release drug delivery, is that being able to control the swelling in a polymer gel is a very important property. And so Fleury and Renner came up with an equation for calculating the swelling of the polymer gel. Essentially what they do is treat the polymer gel using the Flory-Huggins solution theory of polymers. And now what you have is you have one of the materials, the gel, essentially has an infinite molecular weight. And so instead of having terms for its entropy in solution, what's counterbalancing solvation is the extension of the polymer chains, essentially the decrease in entropy upon deforming a polymer chain in the gel or stretching it in order to accommodate a larger concentration of solvent within the material. And so what we see is the Flory-Renner equation relates the molecular weight between crosslinks, essentially the length of a polymer chain between network junction points, to the total length of the original polymer chain. So the concept they use is a polymer chain that's synthesized and then cross-linked after synthesis. And then these molecular weights are then related to the concentration of solvent in the material, the concentration of polymer in the material, phi 2 sub s. So phi 2 sub s is the concentration of polymer with the sub s denoting the swollen state. Chi is the interaction parameter between the polymer and the solvent. So a lower chi is more favorable interaction. And then we have the specific volume of the polymer and the molar volume of the solvent in the material. And so this equation is what allows us to understand responsive swelling in polymer networks. So many of the types of responsive transitions, for example, thermal responsive transitions or pH responsive transitions, can be conceptualized as tuning this interaction parameter chi when you have a fixed chemical structure. Right? The chemical structure is essentially the locations of the network junctions, the molecular weight between crosslinks, and so that's given by MC and Mn. And the parameter we'd like to tune is the fraction of polymer in the gel, so essentially the degree of swelling. And so the way we do this is by tuning the polymer-solvent interaction parameter chi. And responsive changes in that parameter as a function of various thermodynamic variables can swell or deswell the gel and allow this sort of smart material response. Now the swelling in the gel will depend on the condition under which the gel is prepared. And this is one of the predominant characteristics of gels, is that the structure of the network depends on the preparation conditions. So when gels are synthesized from a dilute solution of polymers, they'll have different properties than when a gel is synthesized from a bulk polymer melt, cross-linked, and then solvent is added afterwards. And so Flory and Renner developed their equation originally for cross-linking of bulk polymers, which were then swollen afterwards. Pepys and Ed Merrill, one of our emeritus faculty members here at MIT, developed an equation that can account for swelling in a material that is cross-linked in a solvent and then swollen either in a different solvent or in additional solvent after the synthesis of the gel. And the key modification is that they renormalize certain powers. They renormalize certain powers of the polymer concentration in the gel in the swollen state, which we denote phi 2s by phi 2 comma r, whereas phi 2r is the polymer concentration in the relaxed state. And the relaxed state is the state of preparation of the material. So before the polymer chains were stressed through the addition of extra solvent. And so this Pepys-Merrill equation is a modification to the Flory-Renner equation that allows us to quantitatively model the behavior of gels that were cross-linked in solution rather than cross-linked in the bulk state. Now, one of the challenges of all of the different, let me skip back a few slides here. One of the challenges of these theories of mechanics and theories of polymer swelling is that they make certain assumptions about the connectivity in the polymer network. In particular, what they assume is that all of the polymer chains, and in fact all the ones that we're measuring, and we call these elastically effective chains, are connecting two different junctions in the network. So if I look, for example, at a trifunctional junction point here, and a trifunctional junction point here, I see that this polymer chain right here is actually bridging between these two trifunctional junction points. And we refer to this type of structure as a bridge. However, if I look at this trifunctional junction here, I see that now this chain here connects twice to the same trifunctional junction point. And so this chain is what we refer to as a loop. And because this loop isn't connecting two different trifunctional junction points, its response mechanically will be significantly different in the gel. And so one of the things that we consider in gels in terms of understanding their structure is what is the ratio of loops and bridges, and how is this potentially impacting the way that the gels will respond mechanically. And so I wanted to briefly mention, this has traditionally been a very, very challenging problem because it requires taking a very large, very structurally diverse and sort of messy molecule and looking inside it to count its small length scale structures. And so I want to feature a piece of work that was recently published by one of my colleagues over in chemistry here, where he's come up with a way to chemically degrade polymer networks, and using this chemical degradation, he can then understand what the fraction of loops and bridges is. So this is from Professor Jeremiah Johnson's group in our Department of Chemistry. What he does is he synthesizes molecules with two different ends, and he uses these as the difunctional molecules to cross-link his gel. So in this case, they're shown with a short end, which is denoted S, and a long end denoted L. And now he's got other versions with one end denoted H and one end D. Basically, they're isotopically labeled. And he uses these to synthesize a polymer network just as you normally would in making a hydrogel. But then what he can do is, after synthesis, he incorporates cleavable groups into the material so that he can chemically or photocatalytically degrade the material, and he breaks it down. And depending upon the type of network junction, essentially depending on how many of the chemical groups react at the trifunctional group, and depending on and whether there are loops or bridges, there's a different probability of having combinations of short and long ends going into that junction. And so essentially you'll see different combinations of long, so he shows here, for example, 3 long ends going all into the same junction cannot happen if you form a loop. Because if one chain reacts twice, you have to have a minimum of 1 short end. You either have to have 1 short end and 2 long, or 2 long and 1 short. But you can't have 3 long and you can't have 3 short going into the junction if one chain reacted twice. And so decomposing this network and analyzing what's reacted at each junction gives them a way to differentiate loops from bridges. And so the piece D shows basically a theoretical prediction of calculating ratios of different parameters, ratios of different combinations of short and long junctions, and then using these calculations, and then these calculations can be used to compare with experimental data. So essentially, Jeremiah developed chromatographic and mass spec methods to isolate these different junction points after a network is degraded, measure their concentration, and then these can be compared with theories developed by Steptoe, rate theory and Monte Carlo simulation, both of which are modified versions of Steptoe's theories that we've implemented. And then these computations agree relatively well with theory. And so this actually provides a prediction for the chemical kinetics of network formation that appears at this level of comparison to be relatively accurate between experiment and theory. Now, before I go on, one of the other major challenges in terms of thinking about gels is that a lot of these analysis techniques, in terms of our mechanical theories and our swelling theories, assume that gels are homogeneous. Right? Certainly there are differences between, there are places with polymer and without polymer. There's some sort of a nanoscopic pore structure, but we're assuming that the gels are mesoscopically or macroscopically homogeneous. And in fact, this isn't necessarily the case. As you can see with the Fleury-Renner's theory of swelling, there will be some maximum or equilibrium swelling in a gel as a function of its chemical design. If during the synthesis of the material crosses over from being below its equilibrium swelling to above its equilibrium swelling, then when the material crosses over, solvent will be forced out of the gel in order to go to the equilibrium level of swelling. This sort of deswelling during syneresis, during synthesis, as crosslinks are added, is known as syneresis and can produce macroscopic inhomogeneities in gels. And this is one of the reasons why many gels appear cloudy as opposed to clear. These inhomogeneities in solvent to polymer distribution can result in light scattering, and this is one of the structural aspects that will be very, very important to characterize with neutron scattering. Alright, so in addition to chemically cross-linked gels, which essentially can be treated as ideal elastic solids, we can also think about physically cross-linked gels, where we have strongly persistent physical interactions that lead to the formation of these network structures. And I've shown here an example from my own postdoc work, which was published several years ago. This is for a simple protein gel, but it shows a very typical mechanical response for a physically cross-linked gel. What you have is that at high frequency, in an oscillatory shear experiment. You have a very flat elastic modulus as a function of frequency, and this is what's often referred to as the modulus of the gel in the literature, although I think certainly in detailed mechanical studies we know that this must depend on, this modulus must be a frequency-dependent property. As we go to slower and slower frequencies, such that the frequency starts to be of the same order as the relaxation time of the bonds in the network, then we see the elastic modulus start to drop. We observe a peak in the viscous modulus and a crossover to a terminal region at relatively low frequency. In many of these physical gels, when you apply large strain, and this is a strain sweep shown in piece B, you see a broad linear region followed by a region where the moduli apparently drop and the shear stress, shown here in green, peaks or may plateau, essentially indicative of some sort of a yield or fracture behavior in the material. And so this is one of the characteristics of physical gels, is that their linear elastic network structure can be broken down by the application of force or by responsive transitions that cause crosslinks to form and break. This gives us another mechanism of tuning the response of the materials through changes in the molecular level associations and structure of the hydrogel material. And so this is one of the bases for producing shear thinning materials, and also a basis for producing self-healing materials, where the spontaneous reformation of cross-linked structures after the application of shear or after a responsive transition can enable a transition from liquid-like behavior to solid-like behavior in these types of materials. All right, so models for association in these, models for the mechanical response of these types of physical associating structures have been studied by a number of groups. One of the earliest works in this area was by Tanaka and Edwards back in 1992, and they essentially develop a paradigm for modeling these associative networks. So the idea is that you consider one of these, a network as essentially a number of polymers which are linked together by reactive species. So we consider the physical junction as a chemically reactive species that has some equilibrium based on its binding energy, some equilibrium constant of associated and dissociated states. When you apply a force to one of these network junctions or strands, then according to the concept of Bell's law, this force accelerates the breaking of the junctions, or under deformation. And so deformation can accelerate the breaking of the junctions and the rearrangement of the molecular structure. And when one considers, a recent theory published by Tripathi and McKinley considers this in an advanced level. And what you see here is a comparison between this type of theory and experimental data that I've shown that's similar to the protein gel data I discussed earlier, where we have this high frequency plateau modulus, a peak in G prime, double prime with lowering frequency, and a terminal region at the lowest frequency. What you see here is that the symbols are data points for studies of a hydrophobically associating polyurethane material, both in steady shear on the right and in oscillatory shear on the left. There are two different molecular weights on the top and on the bottom. And then what you see in the solid lines is the comparison to the theoretical prediction from Tripathi, Tam, and McKinley. And the theory actually matches very nicely, capturing all the qualitative features and much of the data quantitatively for these systems. And so this gives us a sense that this idea of physical networks with equilibrium between bound and unbound states, and then force-activated dissociation and rearrangement of a network really effectively captures a lot of the properties of the gels in terms of mechanical response. So I think as a materials scientist, we're very interested in how the structure of these materials, right, how does the arrangement of the molecules in the gel fundamentally impact the response of the mechanical response, these transport properties that we're really interested in and concerned about in the material. And so far we've thought about and conceptualized these polymer gels where all of the junctions in a network are linked together by flexible molecular strands. Gaussian polymers or polyelectrolyte polymers in a buffer or something of this nature. But in the broader sense, there are many different ways to form networks and many different ways to link or connect these networks through different types of molecular or colloidal interactions. And so now I want to pose a broader question of what characterizes the structure of a gel. All right, so things that we've come across so far, the gel has some sort of characteristic mesh size. Right? If the gel is going to contain a large volume fraction of solvent, that solvent is contained in some sort of a characteristic mesh, And through this mesh, small molecules can move very, very rapidly at this small length scale, but then this mesh has a characteristic larger size at which we can envision the gel starting to disrupt the transport of large objects. Right? So there's some sort of characteristic network or net size. The gel has some sort of aggregate structure that's forming this net. So maybe the strands in this net are flexible polymer chains. Maybe they're self-associating fibrils. Maybe they are colloids that are jammed into one another, like Professor Reutz talked about. Or maybe there's some other type of mechanism that we'll discuss in a bit. But this has some sort of characteristic dimension of the network that's forming this net mesh size. Right? On a larger length scale, the gel may be homogeneous or inhomogeneous, depending on how it was formed, what its structure and interactions are. This may be equilibrium or kinetically trapped. And so there's also a large length scale structure to consider in terms of the gel. The interaction between units in the gel, be the units colloids or small molecules or polymers, will fundamentally govern gelation. And these structures can certainly show a strong dependence on their preparation condition and on the concentration under which the gel is being analyzed. So we want to really understanding the structure of the molecules in the gel gives us information on the mechanism by which the molecules are forming the gel, what its characteristic structures are, what types of models will apply for mechanics and transport, and how to really analyze and understand the gel. So neutron scattering is particularly useful for the characterization of gels for many reasons. So I say in the first bullet, gels are inherently rich in water, and what I really should say is gels are inherently rich in solvent, to be much more general than just hydrogels, although I think when I wrote this I had hydrogels on my mind. And because it's so rich in solvent, you can use deuterated small molecules as a way to tune contrast to achieve either very high HD contrast or to contrast match different components in the system. And so there's a lot of flexibility in gels with isotopic labeling because it's relatively inexpensive to purchase many different types of deuterated solvents compared to the complex chemistry for deuterating certain types of molecules. So gels are flexible in terms of their labeling. The second and very important thing is neutron scattering is an in situ technique, and this avoids the artifacts seen in many other types of analysis methods, one of which I'll show you on the next slide. Right? Gels exhibit their properties under a certain condition of solvent, pH, ionic strength, and temperature, and their structure can be very sensitive to changes in this condition. And so analysis techniques that can probe the gels directly under the condition of relevance are very, very important. Neutron scattering is also compatible with in situ mechanical measurements, which I'll say a few words about on Thursday, which I think gives you a broad range of ability to study how structure correlates to mechanical response. Furthermore, many of the materials we're interested in for gels, and particularly in the biomedical literature, where gels such as protein gels or polysaccharide gels are of high interest, many of these gels can show significant sensitivity to radiation such as X-rays. And so the number of experiments, particularly in situ experiments that can be performed on neutron scattering, is potentially broader by virtue of the fact that radiation-induced damage of certain hydrogel materials is significantly less of a concern. And for many of these materials, which are quite precious, because the concentration in the gel of the precious material is relatively low, it's possible to prepare relatively large samples. And so concerns about having to have a larger neutron scattering sample are relatively less with hydrogels than they can be with other types of custom synthesized polymers or small molecules, because you can prepare a large volume of material based on a relatively small weight of the precious component because it contains a large fraction of solvent. So I really want to emphasize this applicability of neutron scattering as an in situ technique which avoids artifacts seen in other types of analytical methods. And so I want to show you on this side, this is an example of bad nanoscale imaging of gels, and you see I don't have a reference here. This is unpublished data from my own group, never to be published data from my own group, but it shows you characteristically what can happen when you try to use certain methods for the structural analysis in gels. So looking at, these are two cryo-SEM images of a protein-based hydrogel. Looking at these two images, this is a structure that could conceivably be a real structure in a hydrogel, but it's actually full of artifact. And the challenge is that during the cryo preparation, so this material was a hydrogel, it's cryo plunged in a cryogen and frozen very, very fast, and then you try to image it at cold temperature on the SEM. The challenge is that during the imaging process, you have to sublime water to see the surface structure. And the sublimation process occurs at a temperature above the vitrification temperature of water, and so the water inherently starts to form crystals during the sublimation process. When this crystallization happens, as it usually does, on a timescale competitive with sublimation, you form pores in the gel that weren't there to begin with. And so we see these sort of 100, 200, 500 nanometer size pores in the gel that form in this cryo-SEM, and these pores are not actually there in the gel. These gels are very optically clear, and they show no signs of pores by other techniques. We can furthermore tell this is an artifact by changing the preparation condition and seeing really the same type of structure with all the different preparation conditions. And so this is an example of having to be very, very careful with microscopy based on the processing methods to not get artifacts incorporated into gel imaging, whereas neutron scattering has this inherent advantage of being able to do in situ measurements, which I think makes it a very powerful technique for the characterization of these types of materials. Alright, so now before launching into a discussion of many different types of polymer gels and how to look at their structure with neutron scattering, I'd like to pause and see if we can have any questions. Well, let's go ahead and continue then. So, in addition to the polymer gels that I talked about previously, there are a lot of different ways to form gels. And so what I'd like to do now is start looking at some of the different types of molecules that people use to form gels, and then how these structures can be analyzed using neutron scattering, and what neutron scattering can tell us about structure in these different materials. And so this slide is by no means a comprehensive list of the different ways and different types of gels, although I think it highlights a lot of the materials that are interesting. The approach I'll take is to examine specific papers from the modern literature that are representative of each of these different categories of gels and look at what they do in terms of neutron analysis and take a look at their actual data to see what we can learn from their type of structural analysis. So one of the types of gels that one we've already talked a lot about to get a sense of the properties of the materials is polymer networks. And so we'll start there. Recently there's also been a big emphasis on the preparation of gels with really emergent properties, high toughness, high extensibility, and double network gels, which are essentially two polymer networks polymerized together in a specific way, are very, very, very interesting, and so I want to mention those. Fibrillar gels are a material significantly different than a traditional polymer gel. So in a fibrillar gel, rather than these flexible molecular strands connecting network junctions, we form fibrils by the self-assembly of generally small molecule gelators. Some of them are proteins, some of them are pi bonders, some even very, very small peptides, for example, with optically active functionalities connected to them. Some can be hydrogen bonding moieties, or some can even be lipids. They self-assemble into long fibrils, and the fibrils can form either defects that result in junctions or physical entanglements around one another, or some combination of the two that result in gelation in the system. Furthermore, we can have block copolymer gels, essentially copolymers, where the tri-block copolymers, where the mid-block is highly swelling with solvent, and the swelling of this mid-block results in the formation of a gel. We can have colloidal gels. I think some examples of this were discussed in earlier lectures, where particles can jam together and form a rigid structure that makes a percolating network. And then a final example that we'll have time to touch on, not this time but on Thursday, will be nanocomposite gels, where essentially you have flexible polymer chains mixed with inorganic particles such as clay or silicate, and these then form a highly hydrated gel structure that can potentially have interesting mechanical properties and responses, and a structure that's amenable to characterization via neutron scattering. All right, so the first example I want to discuss is an interesting and new example of end-linked polymer gels. And this has been developed by Mitsuhiro Shibayama's group and published recently in the literature. What Shibayama's group did was develop two different types of 4-arm PEG star polymers. And so one is shown here labeled A, and the second one is shown here labeled B. And so polymer A is functionalized on the end with an amine, an NH2 group. And polymer B is functionalized on the end with an NHS ester group. this COO, NO2 with 4 carbons right here. The NHS ester group is an activated ester. This ON, the nitrogen, the ON bond makes a relatively labile ester, and so this ester is particularly reactive with amines, which can attack at the carbonyl in order to form a rapid and selective reaction. So what Shibayama's group does is by blending these two molecules together, the two 4-arm stars can only react with one another. Amines can't react with amines, and NHS esters can't react with NHS esters. So they create materials where they eliminate coupling of two of these arms together to form a loop joined to the same network junction. And they can really only form bridges between two different network junctions. So this sort of end-linked Tetra-PEG polymer gel gives them a way to get closer to an ideal polymer gel than you can with many systems. And so this getting closer to ideal polymer gels has been shown to improve things like the strain and stress at fracture in hydrogel materials. But I select this here for discussion of their neutron scattering results because I think this is a really nice model system. As they get closer to an ideal network structure, then we should be able to make comparisons with the theories of neutron scattering and the neutron scattering equations that have been developed specifically for hydrogels based on assumptions of ideal gel structure. And hopefully they match very, very well, which would give us information, I think, that these are the right sorts of functions. So featured in Shibayama's paper is essentially a derivation and discussion of Sand's equations for polymer gels, ideal polymer networks, which we won't have time to go through fully in detail, but I want to show the key equation for modeling the scattering intensity from this type of polymer gel. And it basically contains 3 pieces. One is a prefactor, which is related to the scattering length density, the concentration of polymer in the gel, and an osmotic factor, which is given below. This osmotic factor is essentially very closely related to the equations we use to predict swelling in the polymer gel. This is basically an adaptation of the Merrill-Pepys equation that we saw earlier. And so all of these factors come out, as prefactors in the scattering of the gel. And essentially this has to do with the relationship between the Q equals 0 scattering and the thermodynamics of gel swelling. There are 2 other terms. One is an Ornstein-Zernike function, which has essentially one of its parameters as this Greek letter C, which is the correlation length. This function, this Oz function, represents thermal fluctuations at short length scales. So this is the fluctuations on the order of these pores in the net or meshwork of the polymer gel, the fluctuation of the polymer chains and the fluctuation of the junction positions. Now, in many polymer gels, you also have this larger length scale inhomogeneity, essentially areas that are solvent-rich and areas that are solvent-poor. Due to this syneresis effect, for example, or due to kinetic effects during gel synthesis that lead to trapping of a sort of arrested phase-separated structure within the gel. And this sort of macro-scale inhomogeneity is captured by a second term, which is a squared Lorentzian. And so you see that this squared Lorentzian essentially has a q to the 4 scaling. The Oz function essentially has a q squared scaling. And then down here, the osmotic factor, the second equation, is essentially related to, again, this Pepys-Merrill equation. This is capturing the equilibrium swelling of the gel according to our well-known equations of hydrogel swelling. So in the network synthesized by Shibayama's group, the fact that they're forming an ideal network not only means that we should be able to compare very well with this form of the equation, but also the ideal network is inherently lacking in macroscopic inhomogeneities. They form it under conditions where they get very, very uniform cross-linking without any sort of arrested phase separation or syneresis during synthesis. And so this leads them to be able to do a fit to the gel structure while completely neglecting the squared Lorentzian term. And so this is what you see on the next slide. These are Sand's fit to end-linked PEG gels over a very wide variety of different conditions. So they have here a Tetra-PEG gel at 10K, Tetra-PEG gel at 20K, so 2 different molecular weights of the PEG arms. And then what you see is fits as a function of concentration of the material in the gel. And so that's shown here down in the legend. And what you see is very strong agreement between just the equation with just the Oz function without the squared Lorentzian function over a wide range of concentrations. At the very lowest concentrations, they fit instead with the form factor of a star polymer. In these conditions, you're really below the gel concentration, and so what you're seeing is just the structure of individual star polymers in solution, rather than these gel sort of network structures that become apparent at higher concentrations. And what you see makes sense is that as the molecular weight of the Tetra-PEG gel increases, then the concentration at which they can fit with the gel structure function also increases. So they can get to essentially they can make gels at a lower concentration, is one of the things they see in their Sands curve. Now, in the case where you can neglect the squared Lorentzian term, you can show theoretically that you can collapse the Sands data from the gels all onto master curves. And so they also show this. And so I've shown here two figures from their paper for the different Tetra-PEG gels, showing that when the data is properly rescaled based on the correlation length and the concentration in solution, then you can actually collapse all of the Sands structure, all of the Sands scattering intensities onto these sort of master curves. And so this indicates basically a universal equation for gel structure. All right, hang on a sec. We just got a question. Let me see if I can answer it. So the question is, why is the scattering intensity decreasing with increasing molecular weight of the PEG arm in slide 22? Right. So let me try to find a couple of data sets where we can make an exact comparison of that. So we see, I think, looking at this circle trace and this circle trace, these are two both at 5 mg per mil. Let me try to read this off. So we have about, this looks to me like an intensity of about 7 here. There's 10, 9, 8, 7. About 5, about 0.5 versus about 0.7 here, so a small decrease in that intensity. And at the higher concentrations, you certainly see some bigger changes in some of the symbols. So in these symbols, you see a slightly higher change. So when you look at the equations, so there's certainly some change in intensity between the different PEG arm molar masses. When you look back at the equations on slide 21, what you see is that the intensity is being modulated by this prefactor. Right? So when you're looking at the intensity as you go towards towards Q equals 0, which is what I'm inferring you're meaning from your question, Ming, is that this is applying to, this is essentially derived from the equations from this prefactor term, which is then given by this gel swelling parameter. And so this will depend on a variety of different parameters, molecular weight between cross-links, the concentration in the gels, which is controlled for here, molar volume of solvent, which is also controlled, but the molecular weight between cross-links is particularly coming in to the computation in these equations, and then also any sort of effect of gel swelling during preparation is also coming in. Hopefully that answers the question you were trying to ask. Now I want to move on and talk a little bit about these double network type of materials. So this is a couple of figures that are absolutely fascinating, excerpted from a paper by Jianping Gong, where she originally disclosed the ability to make these types of double network polymers. So there's two columns here. One is PAMP, so polysulfonated styrene, a sulfonated polymer, and the second one is a double network of acrylamide and a sulfonated polyelectrolyte polymer. And what you see is that in the polymer network with just one single network, the gel is compressed, and when the gel is compressed, it fractures in a brittle manner. And so this is intuitively what you're used to seeing in materials like Jell-O that you normally eat. If you take Jell-O, the food, and crush it, or for example, if you take jelly and crush it, then you see that the material fractures in a brittle manner and breaks apart. And when the compression is removed, essentially when the plates are moved apart, then what you see is that the material is completely failed. In a double network hydrogel, something qualitatively different happens. Here's the original material. Now it's compressed in the middle panel, and so you see it hasn't fractured yet. Then finally, when the compression is released, when the compression is released, the gel springs back to its original shape. And so this is pretty fantastic. Something that would normally fracture a gel, compression to a very, very high deformation, doesn't. And so this doesn't say that there hasn't been a microscopic change in the gel structure, but macroscopically the gel is able to recover and maintain its mechanical integrity even after a large-scale deformation. Another example shown on the right-hand side shows a gel being cut with a blade. In the single network gel, you can see that a cut actually forms within the material. And in the gel with two networks, what you see is that when the blade is pushed into the gel bends, essentially resisting cutting by the blade. And when the blade is pulled back, now there's really minimal damage or deformation to the surface of the gel. And so this double network concept is essentially a way to form gels with extremely high mechanical toughness. And so the way this was done was essentially one polymer was polymerized to form a single network, the PAMPS polymer, and then within this PAMPS network a second polyacrylamide network was polymerized, where this polyacrylamide network forms essentially with no chemical bonds between the two networks. But when the networks coexist in the appropriate way, you can get to this very, very high mechanical toughness essentially by the interweaving of the two networks together. And neutron scattering can give us some insight into particularly why this mechanism leads to toughening in these types of hydrogel materials. But before we go on to that, we have a follow-up question from Ming, who asks, what is the meaning of M on slide 21? Right, M is essentially an osmotic molecular weight. This is related to the osmotic pressure in the material, and appears essentially in place of from slide 21. This is related to the osmotic pressure within the material, but M is basically called an osmotic molar mass, yeah, that's more or less it. All right, so looking at these double networks, then a collaboration between some folks in NIST and folks in Gong and some other researchers was able to use neutron scattering to elucidate what was happening to the structure of these hydrogels under deformation. And so I've shown here the experiment that they performed. They took two quartz windows and put a double network hydrogel between the two quartz windows. And then they shear the two quartz windows past one another. And the reason they do this type of experiment is to try to minimize the formation of fractures or cavitation within the hydrogel material during deformation, because these sort of fractures or cavitation would be strongly scattering to neutrons, essentially the contrast between the gel and air or vacuum in the material system. So to try to analyze the weaker contrast they expect from network structure changes without this interference, they do this sort of shear experiment. What they find in panel B is that when they shear that, so when they start out with the gel in an underformed double network gel, analyzed by neutron scattering, these are the red symbols on the graph, they see a relatively low value for the low Q scattering. But upon deformation, they see a big increase in the low Q scattering, and they've analyzed this in two directions, parallel to the elongation direction, and normal to the elongation direction, and what they see is that parallel to the elongation direction, they actually see an increase in the low Q scattering and the formation of a peak in the material. And this peak is indicative of a correlation length that's formed within the structure of the gel, and that's not present in the gel as prepared. So as prepared, essentially the two types of chemical networks are homogeneously distributed throughout the material. But when the material is stressed, the distribution of the networks becomes inhomogeneous. Essentially, one of the networks breaks apart at some regular length scale, and this length scale is observed as the correlation length in the double network hydrogel. And this fracturing or breaking apart at regular length scales in one of the networks dissipates energy that's imparted by the compression of the material. And this energy dissipation provides a molecular mechanism to resist fracture without allowing the fracture to propagate across the entire network. And so it's really this sort of breakup structure that helps to lead to energy dissipation and resistance to fracture. Now, what this implies, for those of you thinking about what this would mean for the mechanical experiment on the previous slide, is that when the gel is deformed, and then it forms these sorts of broken structures on the order of this correlation length. Because the gel was chemically bonded, to form these structures, you need to break chemical bonds. And breaking these chemical bonds will dissipate a lot of energy, but the chemical bonds won't reform when this compression is removed. So when the compression is removed, the intact network pulls the gel back together, but the second network has already been broken. And so if you recompress the gel, you would expect to see a relatively low modulus for compression. And in fact, this is what you see, is that on recompression, the gels don't have the same strength they originally did on their first compression, because there can be some permanent chemical damage within the materials. But this really provides a fantastic way to get extremely high strength, high toughness hydrogels. So the SANS analysis also allows the interactions between the two different networks to be inferred, another important property in these sorts of multi-component systems. Shown here are SANS. So this is also illustrating how contrast matching can be effectively used in SANS analysis. So you can look individually at the acrylamide and the PAMPS networks in the material, both within a double network gel and in just water. And what's seen is that in just water, there's a relatively large amount of low Q scattering, indicative of these large length scale inhomogeneities that are often present in the gel during synthesis. This is, again, the effects captured potentially by the squared Lorentzian term in the gel scattering. When the gels are incorporated into double networks, though, you see a significantly reduced low Q scattering, which indicates enhanced dispersion of the two polymers within the materials, so a decrease in the inhomogeneity of the structure. And so this decrease in inhomogeneity suggests essentially that there are non-covalent interactions between the two networks that are favorable, that are assisting in the homogeneous dispersion of the two different chemistries throughout the material. And so this interaction is potentially key to the way that the molecules distribute and transfer stress between the two networks during deformation. All right, so I think we're getting close to the end of today's lecture. So for the last topic for today, what I want to tackle is looking at what SANS can tell us about responsive or about block copolymer gels. So I have two different examples of work that I think is pretty interesting about using responsive self-assembly in copolymer gels. The first one is from my own group, trying to engineer responsive protein hydrogels with potential applications in tissue engineering. So in this case, what we set out to do was to make at low temperature a hydrogel that would form with just a single network, and in this case a network of associating protein domains, in which we could embed cells or pharmaceuticals and undergo some sort of a shear thinning flow to facilitate injection into the body. After injection into the body, we want the gel to toughen up into an implant, and so our thought was to self-assemble a second polymer network within this material to effectively produce two different networks, a protein network and a block copolymer network, that would then help to enhance the toughness and mechanical robustness of the material. And so I've shown here the molecule we made, which had two thermal-responsive polymer end blocks synthesized from poly-N-isopropyl acrylamide, and then in the middle has a protein domain with these helices illustrated here, where these helices bundled together to form coiled coils or associating bundles, and these associating bundles form the physical associations for the protein domain. Now, following the work of many talented researchers before us, we apply a Perkusiewicz disordered hard sphere model in order to try to capture this self-assembly behavior in the block copolymer gel. In most of these copolymer gels, the copolymer nanodomains, unlike some of the examples shown to you by Professor Lodge, don't order onto a regular lattice. They're often highly disordered, and so they don't necessarily show a series of scattering peaks that can be indexed to crystallographic structures. So the Perkusiewicz disordered hard sphere model essentially assumes a hard sphere interaction potential between particles and uses a Perkusiewicz theory to apply closure to calculate structure factor for this material. So the scatter intensity is modeled as a prefactor, which includes factors such as the scattering contrast, a structure factor of the material, which comes from the Perkusiewicz, F of Q, a form factor for the material, which is essentially a spherical form factor for the spheres in the system, and a constant factor C, which accounts for incoherent scattering from the material. So for the disordered hard sphere model, the Perkusiewicz equations are published, and so I show here the equation for the structure factor. This includes two different parameters. One is a parameter eta, which is essentially the packing fraction of the spheres, and one is a parameter capital R, which is essentially the hard sphere radius of the particles packing in the material. An important thing to note, particularly in hydrogels, is that the hard sphere radius isn't necessarily the radius of this particle that's being formed by self-assembly. Right? This may be a separate parameter that we have to consider. So two parameters, packing fraction and hard sphere radius. G of 2QR is then given by this function shown here with different constant coefficients, alpha, beta, and gamma, which are all a function of packing fraction eta. Now, one important thing to note is that for many of these copolymer systems, the Perkusiewicz disordered hard sphere model has to incorporate polydispersity in the spheres in the system. And so you can incorporate polydispersity essentially by averaging over the size-dependent form factor for a given sphere. And one of the differences you see so essentially we use this integral averaging over radius of the sphere with the form factor with the function for an individual sphere, and by averaging over that we obtain the polydispersed form factor for the material. Now, one of the things we see is that in the literature there are many different choices of probability distribution that can be used to model the polydispersity, and it's generally a polydispersity distribution has to be assumed because it's difficult in order to obtain external validation of your choice. Now, in our case, we assume a log normal probability distribution in contrast to a Gaussian probability distribution, because the log normal distribution avoids challenges with getting negative sphere radii if one of the tails of your Gaussian distribution crosses across 0. And so this is potentially a nice choice in terms of doing modeling. So I show here on the right-hand side of the slide an example of the scattering from one of these gels in the self-assembled state, where here we have the blue dots are our SANS data, and then the red line is the fit with this Perkusiewicz disordered hard sphere model with polydispersity. The structure inferred by the model is shown in part A, where we have three parameters, D, which is essentially a distance between the molecules, capital RHS, which is not between molecules, D is the distance between two different self-assembled domains, RHS is the hard sphere radius, and then R naught is the core radius, or the radius of the self-assembled polymer aggregate. Right? The packing fraction can be related to essentially D and the hard sphere radius, RHS, and so by fitting the packing fraction in RHS, we can extract D, the distance between the spheres in this system. And so you can actually analyze the evolution of all these parameters as a function of temperature in an example material, which I've shown here. So as we heat the materials up, we go from a state where all of the polymers are dissociated to a state where all of the polymer end blocks associate and self-assemble. And so what you see is that at very, very low temperatures, we essentially no longer fit to the Perkusiewicz model, but as we start to assemble, we form at a characteristic initial sphere size at low temperature. The hard sphere radius of these particles grows with increasing temperature, and so this counts not only the core of polymer, but the shell of gel around it that produces an effective hard sphere interaction. You see the packing fraction grows very rapidly from near 0 up to a peak value and then decreases very, very slightly as we continue to increase temperature. And the core radius grows and then reaches roughly a plateau value where it's growing only very slowly with increasing temperature. You see some significant noise in the estimation down here at low temperatures where the fit to the data is much more challenging as the structure is poorly developed. And so really neutron scattering then gives us a powerful way in situ to measure the temperature evolution of the materials as we heat them through the structural transition. We can then correlate these structural transitions with mechanical response, and what we actually show is that to maximize the increase in modulus and the increase in toughness in these materials, the key is not to maximize the temperature where we have the best developed structure, but really to maximize the packing fraction eta. So we essentially can go to these intermediate temperatures where the packing fraction is maximized, and this gives us the ability to get the types of mechanical properties that we're interested in, the highest possible toughness and the highest possible modulus out of these materials. So what I want to do then today is just finish, for a few more minutes, just finish one more example of these block copolymer gels. This is from Ken Schell's group in Northwestern University. So Schell's group on slide 32 has prepared an example of another example of responsive sol-gel transitions based on block copolymers analyzed by neutron scattering, where in this case they use polymethyl methacrylate, block poly-N-butylacrylate, block polymethyl methacrylate, tri-block copolymers, and illustrate schematically the phase behavior here, where the materials are heated. As the materials are heated, they transition from an elastic solid to a viscoelastic liquid to a fully dissociated low viscosity, high temperature fluid phase. And shown on the right-hand side of this graph, again, are the neutron scattering curves measuring structure in these materials as a function of temperature. And so as the material is cooled down, so we have the highest temperatures on the bottom here, as it's cooled down, you start to see the growth of structure. And then at the highest temperatures, very well-formed peak with shoulders, characteristic of the Perkusiewicz hard sphere model. And so Schell fit his data in this manuscript also with the Perkusiewicz disordered hard sphere model, which is very common for these sorts of block copolymer gels with spherical aggregating domains. And here's an example of the fit shown here on the left-hand side of the structure. On the right-hand side, I show, again, the ability to extract average domain spacing d, this distance between two aggregated domains in the gel, and then also based on calculations of the size of the domains, the average aggregation number g can be estimated from the size of the core of the domains, showing trends in the aggregation number and trends in the domain spacing in the fully developed gel structure with changing the polymer concentration, phi p, in the gel. And so they essentially show that as you increase polymer concentration in the gel, the domains get closer together and the aggregation number of each individual domain increases. All right, so at this point, before starting a new topic, at this point I'd like to stop for the day, have a chance to answer any additional questions, and then continue with the remainder of this stuff on Thursday. Thank you very much, and look forward to having an opportunity to speak with you again on Thursday.